Welcome to the deep dive. We're here to help you cut through the noise and really get up to speed on important topics without feeling overwhelmed.
Yeah, making complex stuff accessible.
Exactly. And today we're tackling something central to AI, how these models actually classify information, how they sort things out accurately. It's fundamental to so much tech we use.
Absolutely.
Hmm.
And getting that accuracy right is a huge ongoing challenge. The materials we looked at for this dive really dig into that, comparing different AI mindsets almost, and this interesting two-stage filtering idea.
Right. We've got info on these different models, what they do well, where they maybe struggle a bit, and also how just adding more categories for them to sort through changes things.
Yeah, it's not always straightforward.
And we've included a YouTube link too if folks want to see more.
Good idea.
So, our mission today basically is to unpack the trade offs involved in these AI classification methods, why some are better at certain things, and how this multi stage system tries to get, really high reliability.
Okay, let's get into it.
Okay, so the sources talk about two main ways of doing things. First up, there's model set A. This one classifies stuff into 29 different categories.
Hmm.
Then you've got model set B, which bumps that up quite a bit to 47 categories. So right away, you see a difference in like the level of detail they're aiming for.
Yeah, and what's really interesting is how they're described. Model A is called the sensitive detector, and Model B is the cautious discriminator.
Sensitive versus cautious.
Right. It points to different philosophies, different ways they approach the task.
Totally. Model A, the sensitive one, sticking with those 29 classes. Model B, the cautious one, tackling the bigger set of 47. And that difference, well, it really affects how they perform downstream.
It really does.
Yeah.
One key thing to understand here is recall. Simply put, recall is about whether the model finds the things it's supposed to find.
Catching the right stuff.
Exactly. And Model A, being sensitive and dealing with fewer classes, usually has high recall. It's good at not missing things. Think of like a smoke detector that's maybe too sensitive.
Right, goes off for burnt toast.
Yeah, but it definitely won't miss a real fire. It casts a wide net.
Okay, makes sense. Casting a wide net. But the flip side is catching stuff you didn't mean to catch. That brings us to precision, right? And that's where Model B, the cautious one, comes in.
Precisely. Precision asks, of all the things the model flagged, how many were actually the target? Model B. Because it has that finer understanding across 47 categories, it tends to achieve higher precision. It's more accurate in its positive identifications.
Like maybe an expert archaeologist, less likely to mislabel a find because they know all the subtle differences.
Good analogy. They're careful, more discriminating.
Okay, so boiling it down. Model A, fast, sensitive, catches a lot, but maybe some false alarms.
High recall, lower precision sometimes.
And Model B, more accurate, fewer false alarms, but might miss some things because it's being so careful.
Exactly. Lower recall potentially, but higher precision.
And this trade-off, this is why the research looks at combining them in that two-stage filter.
That's the core idea.
Yeah.
You don't necessarily need one perfect model if you can combine their strengths strategically.
Okay, so how does that work? Stage one uses.
Stage one uses Model A, the sensitive one. The goal there is high recall, find anything that might be relevant, broadly identify potential unknowns or targets.
Like an initial screening. Flag anything suspicious.
Exactly. Then stage two brings in Model B, the cautious, high-precision model.
Ah. Oh.
Its job is to look closely at everything flagged by Model A and accurately classify it, filtering out the false positives that Model A might have generated in this wide sweep.
Gotcha. So Model A makes the first cut, maybe a bit messy. And Model B cleans it up, makes the final, more accurate call.
You got it. It's like maybe airport security. The first metal detector is super sensitive, beeps for keys, belt buckles, everything.
Right. High recall.
Then the secondary check, maybe the X-ray or a pat down,
Yeah.
that's the high precision stage to figure out what actually set off the alarm.
Okay, that analogy really helps. First the wide net, then the focus check.
By sequencing them, you're aiming for a system that's both sensitive and accurate overall. More robust.
Now, the sources give us this email example, which is great for making it concrete. Let's walk through that. Say 100 emails total,
Okay?
and 10 of those are actual spam.
Right. Now let's imagine Model A, our sensitive first stage, scans these and flags 15 emails as potential spam.
Okay, 15 flagged.
Now out of those 15, it correctly identified 8 of the actual 10 spam emails. Those 8 are true positives.
Yeah.
It correctly said spam is spam.
Makes sense. But it flagged 15, only 8 were right. So the other 7 it flagged.
Those 7 must have been legitimate emails that got wrongly tagged as spam. Those are the false positives
Yeah.
or, false alarms, over-tagging.
Right. So out of the 90 emails that were actually legitimate,
Uh-huh.
zero point 0.7 got caught in the spam filter by mistake, which means 83 legitimate emails were correctly identified as not spam. Those are true negatives.
Exactly. So now we have all the pieces to calculate those metrics we talked about.
Okay, let's do recall first. That was true positives divided by all the actual positives.
Right. So 8 true positives divided by the 10 actual spam emails. That's 8 divided by 10.
80%. So it caught 80% of the spam.
Correct. Now, precision, that was true positives divided by everything the model flagged as positive.
Okay, so the 8 true positives again, divided by the total 15 emails it flagged. 8 divided by 15, that's just over half.
Yeah, about 53.3%. So only roughly half of what it flagged as spam was actually spam.
Ouch. Lots of false alarms there.
Definitely. And finally, accuracy. That's just the total correct classifications, true positives plus true negatives divided by everything.
So 8 plus 83 divided by 100 total emails.
Yeah.
That's 91 divided by 100, or 91%.
Right. And this is important. 91% accuracy sounds pretty good, doesn't it?
Yeah, on the surface.
But when you look at the 80% recall, meaning it missed 20% of the spam, and especially that low 53% precision, meaning almost half its flags were wrong, well, you see the problem.
Right, the overall number hides the specific issues. That low precision means lots of good emails might end up in the spam folder, which is really annoying.
Exactly. It shows why you need to look beyond just accuracy. You need recall and precision to understand how the model is performing or failing.
Okay, so this really drives home the roles in the two-stage system again. Model A, stage 1, its job is basically maximize recall, right?
Yeah, find as much of the potential target stuff as possible, even if it means being a bit messy with some false positives. Don't miss the spam.
And then Model B comes in for stage 2, focusing on high precision. Sift through stage 1's output, weed out those false alarms, and make the accurate final call.
Precisely. Minimize the frustration of over-tagging.
So the advantages, disadvantages are clear. Model A minimizes misses, high recall, but risks false alarms. Model B minimizes false alarms, high precision, but risks missing things.
You've got it. It's always that trade-off.
Now, the sources also hammer home the definitions of these error types, which is helpful. Let's quickly recap them. False positive or over-tagging.
That's when something normal gets flagged as abnormal, like a perfectly good product being called defective.
The consequence being waste, or maybe inconvenience, like our email example.
Right, then true positive. That's the goal. The system correctly identifies something abnormal. The broken item is caught. The spam email is flagged. Detection ability.
That's what you want.
And then the risky one, false negative or misdetection.
Ah, right. This is when something abnormal slips through as normal.
Yes. The broken item passes inspection. The dangerous email lands in your inbox. The sources highlight the risks here. Safety issues, security breaches.
Yeah, those consequences can be much more severe than just inconvenience sometimes. It really shows why balancing these errors is so critical.
Absolutely. And the formulas help quantify that balance. Precision, TP, TP plus FP. Out of everything flagged positive, how many were actually positive?
Got it. And recall, TP. TPL plus FN. Out of everything that was actually positive, how many did we catch?
Understanding those helps you tune the system based on whether it's more important to avoid false alarms or avoid missing things.
Okay, so let's just lock down this optimal design Model A followed by Model B. Why is this sequence the winner?
Well, like we said, Model A, Stage 1, high recall. The purpose is explicitly to cast that wide net, grab almost all the potentially interesting or undefined samples. You expected to catch most things needing a closer look.
Even if it grabs some extras by mistake.
Exactly. Then Model B, Stage 2, high precision. It acts as that crucial filter. It examines everything Model A flagged, and its whole job is to minimize the false positives from Stage 1. Get rid of the noise.
So you get the benefit of A's sensitivity without paying the full price and false alarms, because B cleans it up.
That's the idea. Leverage sensitivity first, then apply accuracy. A more reliable result overall.
Okay, clear. Now, the last big point from the sources was about what happens when you increase the number of categories, C, that the model has to handle. This was pretty fascinating.
Yeah, it's not as simple as more categories equals better classification.
Right. You'd think more detail would be good.
But when you increase C, the feature distance between categories often gets smaller. The differences become more subtle.
Like trying to sort 50 shades of gray instead of just black and white.
Exactly. The boundaries get way more complex, more fuzzy, and that means the probability of misclassification just goes up. It's easier to make a mistake when things look very similar.
Okay, that makes intuitive sense. Harder distinctions lead to more errors. What else?
There's also this effect of increased overconfidence in wrong answers.
How does that work?
Well, the model has so many categories available, it might feel like compelled to assign a sample to one of them, even if it's not a great fit. And it might do so with high confidence, just because it found the closest match among many options.
So instead of saying, I'm not sure, it just picks the least worst option out of 47 and acts sure about it, even if it's wrong.
Sort of, yeah. It forces a fit, potentially an incorrect one, with undue certainty.
Interesting.
And a related issue is that the detection of genuinely undefined or novel things goes down.
Right.
Because the model is trained on, say, 47 specific things. When something truly new comes along, instead of recognizing it as unknown, it's more likely to try and force it into one of the 47 boxes it already knows.
So its extensive training on known categories makes it less able to spot something truly outside its experience.
That seems to be the tendency, yes. It overfits to the known categories, in a way.
Okay, so let's recap the impact of more categories. Finer distinctions, harder boundaries, more misclassifications likely,
Uh,
increased tendency for the model to be overconfident, even when wrong,
right.
and counterintuitively, a decreased ability to spot something genuinely new or undefined.
Exactly. The sources summarize it nicely. Feature distance narrows, boundary complexity goes up, misclassification risk increases, overconfidence goes up, contributing to errors, and undefined detection goes down, meaning novel stuff gets missed or mislabeled.
Wow, so it really underscores this fundamental tension in classification getting more specific versus staying robust and accurate, especially with unexpected inputs.
Absolutely, it's a core challenge. And that really brings us to the end of this deep dive. The big takeaway, I think, is really appreciating that trade-off between sensitivity or recall and accuracy or precision.
Yeah, understanding that you often can't maximize both simultaneously in a single simple system.
Right. And seeing how that two-stage approach is a pretty smart way to try and balance those competing needs. It's like that security checkpoint analogy. Again, the initial broad sweep, then the focus check, working together,
Minimizing both missed threats and false alarms.
which leads to a final thought for our listeners to maybe chew on. Thinking about how these AI models work, this classification challenge, what other real-world systems, maybe even outside of tech, could benefit from a similar layered approach? Where you have an initial broad detection phase followed by a more precise refinement. Where could that help avoid missing critical stuff or getting swamped by noise and false alarms? Something to think about beyond just scam filters.